Good morning, this is Dr. Olson for Physics 1053, College Physics 1 at Daytona State College. We just finished Chapter 6 on work and energy, and another topic that we usually use with work and energy is linear momentum, and that is the topic of this video. It's the topic of all of Chapter 7. So this and the next couple of videos will address linear momentum. We'll first of all start talking about what momentum is defined to be and how it is related to normal forces that we discussed in Chapter 4. Then we'll discuss the principle of conservation of momentum, how your total momentum doesn't change as long as you have no external forces. Then we'll talk about the different types of collisions you can have and impulses. And we'll look at collision in one dimension and then collision in two dimensions. Okay, so what is momentum? First of all, momentum is simply a vector. It is a vector symbolized by the small letter p, and is calculated as the product of mass and velocity. Now this gives us a really interesting relationship because you remember that force is equal to mass times acceleration. But acceleration is change in velocity over time. So if you take the change in momentum over time, that would be change in mass times velocity over time, or mass times acceleration, which is force. So that gives us this new definition that force is equal to the change in momentum over the change in time. Now, here's what's so cool about this. If there are no external forces, in other words, sum of forces is equal to 0, then that means that the change in momentum also has to equal 0, which means that the total momentum does not change during a collision, meaning the total momentum before has to equal the total momentum after. Again, this is only true if there are no external forces. If you have something pushing from the outside involved in a collision, this no longer becomes true. Okay, so your total momentum before would have to be the momentum of each object added together. So for example, we have two balls flying towards each other. Each one has a momentum of mv for each ball separately. Add those together, that is your total momentum. Then inside of a collision, you're going to have transfer of momentum involved in that collision itself, and transfer of energy as well. And so pretty soon, each ball is going to have a different momentum. However, according to conservation of momentum, the momentum of ball A plus the momentum of ball B, when you add them together, should still total up the exact same as what you had before. So total momentum for A and B before the collision has to equal the total momentum for A and B after the collision. This is known as the conservation of momentum equation. All right. So more formally, here's what the conservation of momentum says. It says that the total momentum of an isolated system remains constant. Isolated system meaning there are no forces from outside involved in the collision. So let's look at this picture here. And let's talk about the velocity before and after the collision. Now you have car A on the left, which is moving to the right at a speed of 24 meters per second, and car B, which is not moving at all. We'll assume for this example that both cars are exactly the same mass. Well then, when they collide, they're going to couple and they will move forward together at the same velocity. We're going to call this velocity v prime. So the goal for this is to know what is v prime. Well, we take our conservation of energy equation, which is that the momentum of A plus the momentum of B before the collision is going to equal momentum of A plus momentum of B after the collision. And we're using the prime to indicate the velocity after the collision. Now, starting off, we note that all these masses are going to be the same, since mass A is equal to mass B. The two cars have the same mass. So all of our masses just become plain m in this equation. Secondly, we note that velocity b is 0 since it's not moving before the collision. So this term is dropped off to 0. So our equation simplifies to mva is equal to mv prime plus mv prime, since va prime and vb prime are going to be the same thing. So now it's a matter of simplifying the equation even more. All the masses are equal, so we can just divide the mass out and combine like terms. So on the left we have velocity a is going to equal 2 times v prime, 1 half here are the 2, we have to multiply by half, so v prime is going to be 1 half va, which is 24, so we have a total velocity of 12 meters per second for both cars coupled together after the collision. And that's a brief example of how to use the conservation of momentum equation. Now here's another really great way to explain an example of conservation of momentum. Let's say that you have a rocket. There are no forces at all, and so your total momentum is equal to 0. But then the rocket ignites, and you have thrust coming out of one side. Well, then all of a sudden that thrust has some backward momentum, some negative momentum. But according to conservation of momentum, the total momentum has to be conserved. So the only way to balance out this negative momentum is if the rocket itself has a positive momentum to counteract that. So that's another very good example of conservation of momentum. Now, a quick word about something called impulse. Remember that force is change in impulse, force is equal to the change in momentum over the change in time. If we multiply both sides by time, then we get force times time is equal to the change in momentum. This is the definition of impulse, force times time. And so it's also easy to say that the impulse is equal to the change in momentum. But when we say impulse, we are referring to this part of the equation, force times time. Now, how would we calculate this? Force times time. If you have a graph that has time as your x-axis and force as your y-axis, force times time would be height times width, which would be just an area. So if you look at a curve as a collision is happening, at first there's no force, and then all of a sudden that force gets really large, causes a change in momentum, and then as the objects end their collision, the force drops back down to 0. So you have a graph like this. The impulse then would be calculated using the area underneath the curve, as we just described. Now, thankfully, we have a shortcut with this, because calculating the area under a curve is not easy unless you have experience with calculus. So here's a shortcut. Assuming that the time is short enough, then we don't need to worry about exact time or exact force. What we can do instead is use average force and the change in time between the initial impact and the final point of the collision. So if we take that area, force times change in time, then that will be a very good approximation of the area under the curve, very good approximation of what the impulse is. Now, why is this impulse important? Well, the impulse tells us that that if we have a large force with a short time, we're going to have a certain change in momentum. But if we reverse that, and instead of a large force, we have a small force over a longer period of time, we can achieve the exact same change in momentum. Good example of this, jump off of a large object onto the ground, keep your knees locked, you have a large force, you have a force, but it's a very, very short change in time. So in order to stop, you have to have a certain change in momentum. Well, if your knees are locked, you have a short change in time, that's going to result in a very large force in your knees. that force is going to be too large for the knees, and you're going to have knee problems from jumping without your knees bent. But if you do bend your knees, that increases the time. You'll have the same change in momentum, but with an increased time, you'll have a lower force. This is the exact same principle as airbags. Instead of slamming into a steering wheel very fast and very hard, the airbag will slow you down a little bit, increase the time, so that when you actually do hit the steering wheel, the force is smaller and damage will be lessened. Okay. Now, whenever you have a collision, two objects hitting each other, we can always say that momentum is conserved. However, we can't always say that energy is conserved. Sometimes we can, sometimes we can't. If energy is conserved, then likely these velocities will be similar to what they were before the collision. That's a minor point. The important thing here is that if the energy is conserved in a collision, then we call it an elastic collision. But if there is a loss of energy in a collision, it would be inelastic. There are a handful of things that can cause a difference in energy. For instance, if you have a collision and as a result of the collision, heat is released, then that means energy is lost, so obviously it will be inelastic because energy is not conserved anymore. Another good example is when you have two cars that hit each other, a lot of the energy in those cars, in fact the majority of it, is put into misshaping the car, crumpling up the front end of the cars. That energy is then expelled, which means energy is not conserved. It becomes an inelastic collision. So let's say that we have two objects that are hitting each other. They are going to hit each other elastically. We know their masses and we know their initial speeds. But we know that both momentum and energy are conserved since it's an elastic collision. So we can use these two equations to help us solve this problem. Change in momentum equals 0 and change in energy equals 0, or conservation of momentum and conservation of energy. With these two equations, we can solve for both the velocity v prime A and v prime B. However, in an inelastic collision, you're going to have energy loss due to thermal or potential energy, or some other kind of energy even. As a result, we could still say that energy is conserved, so we could say delta P equals 0, but we cannot say that energy is conserved, because we know that there was a change in the shape inside of this block, as well as a change in potential energy with the block rising higher in this picture here. So this is a good example of an inelastic collision. Often the objects stick together in an inelastic collision, so you end up having one final velocity, so VA prime is going to equal VB prime, so we generally just say that's V prime. Not always, but this is very typical of inelastic collisions. Now we could do collisions in 2 or 3 dimensions as well. The key to this is knowing, it does get more complicated, but the key is to know that momentum is just a vector, so you just break it into x and y components and solve for vector addition, just as we have in many, many other examples up to this point. Okay, so in summary, we've defined momentum as the product of mass and velocity. Then from Newton's second law, force equals mass times acceleration, we saw that force is equal to change in momentum over change in time. If the system is totally isolated, then your total force is going to equal 0, momentum is conserved. We can use this equation down here at the bottom. And then we also defined elastic and inelastic collisions.